Hi, welcome back to Test Science's series of reliability growth modeling modules. Recall that in the last module, we covered reliability growth models based on the non-homogeneous Poisson process. In this module, we will look at models used to model reliability growth that starts from a different perspective, competing risks. The second common class of models used for DoD reliability growth does not start its development from the NHPP. Instead, these models start from the assumption that the system can be represented as a set of components or failure modes operating in series, which means that all of the components have to be operating, or equivalently that none of the failure modes have occurred for the system to work. And we can visualize this through a string of lights, where each light or component of this system has to be lit or working in order for the entire string of lights to light up. So if this particular light bulb goes out, whether that's because it's burned out, isn't fully screwed in, etc., then the entire string of lights will not light up. And we say that this string of lights is not fully lit or has failed. The idea of competing risks is that each component, or light bulb in this case, is competing to be the cause of failure, and the first one to occur is the cause of the system failure. So this light bulb was the cause of system failure for this string of lights. Within this framework, the reliability of each failure mode is modeled. The models assume that there are a large number of failure modes, K, so we have K lights on this string, that are operating in series so that the system fails whenever one of the failure modes occurs. The time to the first failure of each component, or each light bulb, is assumed to be exponentially distributed with rate lambda sub I. Now, because the system fails whenever any failure mode occurs, the distribution of the time to failure for the system is also exponential, with an overall rate of occurrence given by a sum over all of the component rates, which we denote as the sum from I equals 1 to k of lambda sub I. So before we dive into models, we will talk about system repair. So there are generally two types of systems. Ones we repair or fix, and others we do not repair. Notice we are really only concerned with systems we fix. Since this is the case, we should ask ourselves, how do we account for system improvement after we repair? Well, great question. One way to model this is that when we repair, say our LMTV, the failure rate is changed and hopefully improved by a fix effectiveness factor, which we will denote as FEF sub I. This is the expected fraction of lambda sub I, our rate of failure, removed after our corrective action. Since the fix effectiveness factors are not known, the values used are typically either set based on prior experience or estimated, often using a Bayesian procedure. We won't consider estimating FEF here. We also note that it is usually assumed that no new failure modes are introduced as a result of the corrective action. In other words, in the process of repairing, we aren't causing something else to fail. AMSA planning model based on projection methodology continuous, or PM2 continuous, is a very common reliability growth model that is based on competing risks. PM2 writes the planning curve in terms of tangible parameters that can be influenced by program management, like M sub I, which is the planned initial system MTBF. M sub S is the fraction of the initial failure rate that is addressable by repair. M sub G is the goal MTBF for the system. FEF bar is the average fix effectiveness factor, and capital T is the duration of the test. Now, when we think about M sub S, the fraction of the initial failure rate that is addressable by repair, some of the failure modes will be fixed and some will not, and this may be due to time or budget constraints. We call lambda sub S the sum of the initial failure rates for the components that are not fixed, and lambda sub B is the sum of the initial failure rates for the components that will be fixed. The planning curve for PM2 graphs test time on the x-axis versus MTBF of T. And within this PM2 realm, we estimate MTBF of T through 1 over rho of T. Now this rho of T in this approximated MTBF scenario is equal to this expression here, where we have our lambda sub A, our lambda sub B, FEF bar, and this new thing, H of T. Now, H of T is approximated to be lambda over 1 plus beta sub PM2 times T, or time. H of T is the expected rate of occurrence of new failure modes at time T. These are repairable failure modes at time T. Now, this beta sub PM2 is equal to this expression here, where we see a lot of our tangible parameters that can be influenced by program management. So we have our M sub I, our M sub G, MS, and FEF bar. So what does this mean? Well, for PM2 continuous, starting with competing risks assumptions, the math derives a reliability growth planning curve that can be expressed in terms of program management parameters. So at time 0, the planning curve has value M sub I, the initial reliability. And at time T equals capital T, so the end of the test, the planning curve has the value of our goal MTBF, M sub G. Now, as failure modes are discovered, some are repaired and some are not. Those that are repaired with fixed effectiveness factor FEF sub I. Now this fraction here, M sub I over M sub G, can be viewed as the ratio of anticipated change in MTBF, since we are typically setting the goal MTBF to be larger than the initial, since we want the time between failure to increase. Now we should also note that within the scope of competing risks models, we can also list 2 other models, AMSA maturity projection, AMPM, and AMPM Stein. The U.S. Army has recently specified PM2 continuous as the preferred reliability growth planning model for developmental reliability programs for complex military systems. Hence, we focus on PM2. So now let's visualize a PM2 curve. So understanding that PM2 has these 3 particular equations here, where we have rho of T equal to this expression, which utilizes H of T, and H of T utilizes this beta sub PM2. How do we get a curve from all of this? And how should we understand MTBF in this context? Well, under PM2, we're estimating or approximating MTBF through 1 over rho. And because we're estimating MTBF via 1 over rho, we're utilizing these 3 equations. So this beta sub PM2 that we have here is PM2's way of forming an idealized growth curve utilizing planning metrics like M sub I, M sub G, M sub S, and average FEF. Now, a way to visualize some PM2 curves are through this graph off to the right. Now, when we look at this graph off to the right, we see 3 PM2 planning curves generated for a 2-month testing program, assuming 3 different final reliability goals of 100, 125, and 150. And this is holding the initial system mean time between failure at 50 and MS equal to 1 and system FEF bar equal to 0.7. So all we're doing here is graphing different goal MTBFs to see what kind of idealized planning curve we get. So notice that we can expect MTBF to increase very rapidly early on in the testing period if we set our goal MTBF to be 150, which is this green dashed line. Now, if we look at the red dashed, this is related to the goal MTBF of 125, and this blue is for 100. So we see that the MTBF is a little slower to increase when we're looking at the 125 and 100 goal. And like we said, for the green dashed, which is the 150, we see a very early rapid increase in MTBF. So this is giving us an idea of what to expect should we run a test with 3 different goal MTBFs. We will end this module by highlighting the utility of PM2 continuous. Within the scope of the DoD, we are often taking commands from higher up and need to develop plans in order to achieve desired goals. So when you have some restricted test time, capital T, PM2 continuous provides a way to incorporate your plans through initial MTBF and goal MTBF, the fraction of initial failure repair rate addressable by repair, and average FEF to give us an idea of how we can expect the reliability of our systems to improve, hopefully. Thank you for joining us for Test Sciences series for Reliability Growth Modeling. This module concludes our journey in gaining a better understanding of reliability growth. Please take a look at all of the other materials on the Test Sciences website.